Today we're diving into a paper that I think really changes how we should view large language models when it comes to agency. It's called From Word to World. Can large language models be implicit text-based world models?
Yeah, this one tackles one of the biggest roadblocks for AI agents today. The central question is, can these LLMs, which we know are great at predicting the next word, actually work as reliable, world models, internal simulators?
And the short answer, which is so important for anyone building these systems, is yes. A big yes. But, and this is a huge but, it only works with dynamics-aligned fine-tuning.
That's the whole game. The process literally shifts the LLM's goal from just completing a sentence to actually predicting the next state of the world.
Okay, so what's the big takeaway?
Well, what's fascinating is how the scaling changes depending on the environment. For something really structured like ALFWorld, they master the rules incredibly fast. We're talking maybe 20,000 examples. That's it, they saturate. But then you move to something really open-ended like Stable Toolbench, and the data requirements just explode. You need way more data, a much bigger model.
But once you've done that training, the utility is just massive.
Yeah.
We're seeing models that can hold a coherent state over really long interactions.
And provide real, concrete benefits. Like, they can stop an agent from making a costly, irreversible mistake by verifying an action before it happens.
Which is huge in something like WebShop.
Yeah.
And they can generate synthetic data, which helps solve that experience bottleneck we're always talking about.
Exactly. Plus, they can warm start reinforcement learning policies. That helps stabilize the early training phase and leads to much higher final success rates.
And the models are robust, too. They weren't just memorizing layouts.
Not at all. They really captured the transferable rules of the world. They generalized to completely new environments when they were trained together. That's the dream, right? A single reusable world model.
Okay, let's unpack this from the beginning. We talk all the time about scaling agents, but they always hit this same wall. What exactly is this experience bottleneck that makes a world model so necessary?
It all comes down to the cost of interaction. Think about trying to train an agent in a really complex simulation.
Like WebShop or some embodied task.
Exactly. As the agent gets smarter and the number of choices grows, its need for experience just shoots up exponentially. But getting that experience running real simulations is slow, it's expensive, and it's not very adaptive. It just puts a hard ceiling on what the agent can achieve.
So the world model, or WM, is basically a shortcut.
It's a powerful shortcut. By internalizing the environment's rules, the agent can learn from imagined interactions. It doesn't have to risk a mistake or pay the cost of a real-world action.
How did the researchers actually formulate this? How do you turn a language model into a simulator?
So they did something really clever. They reframed the whole task. They stopped thinking of the LLM as a text generator and started treating it as a function for multi-turn next state prediction.
Okay, what does that mean in practice?
It means instead of just predicting the next word, the LLM takes the entire history of the interaction, the starting state, every action, and every new state so far, plus the current action you want to take.
And it predicts what happens next.
It predicts the new state and the reward. It becomes a functional simulator of that world.
That feels like a fundamental shift. But couldn't you argue next state prediction is just, next token prediction with some fancy formatting?
I see why you'd say that, but the difference is in the objective, in the supervision. Next token prediction learns from passive text. It finds correlations. But next state prediction, when you align it to the world's dynamics, forces the model to learn causal laws.
If I do A and state S, then state S prime must be the result.
Exactly. It moves from being a descriptive tool to a predictive causal engine.
And to test this, they set up a really smart 3-level evaluation framework. It seems designed to make sure they're testing actual utility, not just if the output text looks plausible.
Absolutely. The levels build on each other. Level 1 is all about fidelity and consistency.
So does it predict the next step correctly?
Yeah.
And can it keep that up over a long chain of actions?
Right. Level 2 is scalability and robustness. How does it improve with more data and bigger models? And crucially, can it generalize to things it's never seen before?
And level 3, which is the real so what for any engineer.
Agent utility. Does this world model actually provide a measurable, practical benefit to a downstream agent?
And they tested this across a whole range of environments.
A great range. You've got the structured ones, ALFWorld for embodied tasks, SciWorld for simplified physics and chemistry labs, and TextWorld for quest-like games.
And then the really tough ones, the open-ended environments.
Right. WebShop, which is a simulated shopping site with tons of messy, real-world-like data, and Stable Toolbench, which involves complex compositional API use. That spectrum covers a lot of ground.
So let's start with that first level, fidelity. How did off-the-shelf LLMs do on just predicting the very next state?
Well, the initial results showed that there's already some latent ability there. Pre-trained models like Gemini and Claude, they already have some inherent world modeling knowledge.
From all their pre-training data.
Exactly. Just with few-shot prompting, you could get some pretty decent gains in those structured worlds. The model already has a general sense of physics and, common sense constraints.
So the raw knowledge is there, but I imagine it plateaus pretty quickly.
It does. It hits a wall almost immediately in the more complex settings. In a web shop, for instance, few-shot prompting just couldn't get past the mid-50s in terms of accuracy.
Why not?
Because general common sense isn't enough to predict the specifics of a high-entropy environment. Like, you can't guess what a simulated search engine is going to return. You need to have learned those specific dynamics.
And this is where that critical engineering step comes in. Dynamics-aligned training. Supervised fine-tuning, or SFT.
This was the absolute key. With SFT, even smaller open source models, like a 7 billion parameter Qwen model, achieved just staggering accuracy.
How high are we talking?
99% on ALFWorld, 98% on PsyWorld. It just shows that for a rule-driven world, even a modest model can basically learn the rulebook perfectly.
Okay, so single-step prediction is solid after SFT, but a real simulator has to work over many steps. That brings us to long-horizon consistency.
Right. The consistency ratio, or CR. This is a vital metric. It basically asks if the world model simulates a 10-step plan that works.
Do those same 10 steps actually work in the real environment?
Exactly. If your CR is low, your simulator is drifting away from reality, and it's basically useless.
And for the structured worlds, did the CR hold up?
It did. For ALFWorld, PsyWorld, TextWorld. The fine-tuned models kept CRs above 90% pretty consistently. The simulations were reliable.
But WebShop, I'm guessing, was a different story.
A necessary contrast, yeah. The CRs there were much lower, usually below 80%.
What causes that drop? Is it just the massive number of possibilities?
It's the diversity, especially in things like search results. If the simulated search page is even slightly different from the real one, the agent's next action is based on bad info, and the whole trajectory diverges.
So the simulation drifts. How do you fix that?
Well, they found a clever workaround. They would anchor the rollouts by occasionally grounding the simulation with a real search result from the actual environment. That hybrid approach boosted consistency a lot.
I also thought the link they found between the agent's skill and the consistency ratio was fascinating. A weaker agent, like GPT-4 or Mini, produced a much lower CR. Why is that?
That was a really sharp insight. It shows the world model isn't just modeling the environment, it's also implicitly modeling the behavior of a competent agent.
Because it was trained on expert trajectories.
Right, so when a weak agent does something weird or nonsensical, an action an expert would never take, the world model hasn't really learned the consequences of that off-policy action, and its prediction fails.
So for the simulator to be reliable, the agent using it needs to behave somewhat like the agents that generated the training data. That's a really important design constraint.
It's crucial. Stronger agents stay closer to that expert behavior, so they get higher consistency from the simulator.
Okay, let's pivot to the scaling and robustness findings. This part feels like a practical guide for anyone trying to train one of these models. What did the data scaling laws reveal?
This is where you see that huge divergence again. The structured environments, like ALFWorld, were incredibly data efficient.
They saturated fast.
Very fast. They only needed about 20,000 trajectories to learn the rules. After that, adding more data gave you basically nothing.
And 20,000 is a tiny number in the world of LLMs. What about the open-ended environments?
That's the cautionary tale. A domain like Stable Toolbench showed no sign of saturation at all, even at 160,000 samples.
Why such a big difference?
It's the complexity of compositional tool use, and even more, the long tail of linguistic variation. In ALFWorld, go north is always go north. In Stable Toolbench, there are countless ways to phrase an API call, and the model has to learn the dynamics for all of them.
And I assume the model size requirements followed the same pattern.
Precisely. For structured worlds, the rules are simple, so you don't need a huge model. Even a 1.5 billion parameter model did a great job. But for open-ended worlds, capacity really mattered. You need those larger models to capture all that linguistic richness and complex tool interactions.
So what about robustness? Did the models just memorize the training environments, or did they learn the underlying rules? The out-of-distribution tests in ALFWorld seem perfect for answering that.
It was a great test, and it showed they learned the dynamics, not just the layouts. They tested them on new room layouts and even entirely new types of rooms the model had never seen.
And how did they do?
The world model success rates stayed nearly identical to agents running in the real unseen environment. It proved they captured transferable rules, like how objects and containers work. They are true simulators.
If they're learning reusable rules, that suggests you could train one model on many environments at once.
And that's exactly what they found with cross-environment transfer. When they did joint training on a mix of environments, it consistently sped up learning and improved the final accuracy for all of them.
So you don't need 5 separate world models.
You can build one that's better than any of the specialized ones. It learns to reuse shared physical and procedural knowledge.
Let's bring this all home to the final and maybe most important segment, agent utility. If I'm an engineer, what concrete benefits do I get from implementing one of these world models?
The first, and maybe the most intuitive, is using it as a rewindable safety verifier.
Okay, explain that.
Think about WebShop again. There's one action checkout that's irreversible. If you buy the wrong thing, you fail. Game over.
Right.
The world model acts as a cheap pre-execution check. The agent says, I'm thinking of checking out, and the WM simulates it. If the WM predicts a bad outcome, the agent can pause, rewind, and try something else in the real world.
That seems incredibly useful. Did it actually improve success rates?
It did, across the board. Agents like GPT-4 Turbo saw gains of over 15%. The model doesn't even have to be perfect. It just has to be good enough to catch those critical, costly errors.
So why not just verify every single action? The paper pointed out that more verification isn't always better.
Yeah, that's a super important caveat. They found that a moderate budget, maybe 2 to 10 checks per run, was the sweet spot. If you verify too much, you start subtly changing the agent's behavior.
Creating a distribution shift.
Exactly. The agent's actions start to diverge from the training data because of all the verification steps, and that can actually hurt performance in the long run.
Okay, what about the experience bottleneck? Can we use the WM to just generate cheap training data?
Yes, absolutely. This is the synthetic data generation use case. They generated 1,000 successful trajectories using only the world model and found that the synthetic data was almost as good as 1,000 real trajectories.
Which is a massive saving in cost and time.
A huge saving. But the real magic happened when they mixed the data.
What do you mean?
A mixture of 1,000 real trajectories plus 1,000 synthetic ones actually outperformed either data source on its own. The synthetic data doesn't just replace real data, it augments it.
It adds diversity and coverage for cheap. Okay, and the final utility point was about stabilizing RL training.
Right, early experience for policy learning. This is about giving the agent a head start. Before you even begin standard RL, you fine-tune the agent on the world model's objective.
So you teach it the rules of the world first.
You teach it the rules first. You front-load its knowledge about consequences. This reduced a lot of the early dumb mistakes that agents make and led to consistently higher final success rates. It's like teaching an agent how a door works before asking it to navigate a house.
So to wrap up, this research really makes a strong case that LLMs are more than just text predictors.
It empirically establishes them as learned simulators of interactive worlds, but only with that dynamics-aligned supervision at the right scale. They maintain a coherent state and provide real, tangible benefits, from safety to learning efficiency.
It really reframes the whole conversation. Moving from modeling words to modeling worlds isn't about some brand new architecture. It's about systematic scaling and having the right kind of alignment data. It connects next token prediction to next state modeling as this foundational step for building capable agents.
And it provides a very strong foundation, but within the textual domain. So I think that leaves an important question for you, for the researchers and engineers listening, to think about. We've seen this work for text-based worlds, but what are the challenges in extending this to richer multimodal domains?
Where the state isn't words, but pixels or sounds.
Exactly. When your observations are complex sensory inputs, vision, touch, sound, what kind of data and what kind of model capacity will you need to get the same level of fidelity and consistency? I think that multimodal frontier is the big next challenge that stems directly from these findings.